And now, the topic for our next keynote is AI-assisted reconfigurable intelligent surfaces wireless networks. Our next speaker will present some recent results on the reconfigurable intelligent surfaces wireless networks empowered by AI. In particular, a deep learning-based hybrid beamforming for RIS-empowered multi-hop terahertz communications, AI-assisted MAC, and intelligent spectrum learning with RIS. Now, our next speaker is an IEEE Fellow and Distinguished Lecturer of IEEE Vehicular Technology Society. He received the IEEE Marconi Prize Paper Award in Wireless Communications 2021 and serves as an editor for IEEE Transactions on Vehicular Technology and IEEE System Journal. Now, since 2010, he has been with the Singapore University of Technology and Design. Ladies and gentlemen, let's welcome Professor Yuen Chau.
Hello, good morning for everyone. I hope you can see my screen. Okay, so I'm Prof Yuen here from Singapore University of Technology and Design, Engineering Product Development Pillars. And today I'm going to share with you our research work in this area on the reconfigurable intelligent surfaces for wireless network powered by the AI technology. Okay, let's start. Okay, so this is a typical wireless communication system, a simplified diagram. Over here, you can see in the traditional system with a transmitter go through the wireless channel, and here is the receivers. So in the traditional wireless communication problems, what we try to do is that we try to optimize or design this transmitter and receiver such that we can achieve a reliable wireless communications. And we all know that wireless channel is challenging. So that's why we have to come up with various transmitter and receiver techniques like OFDM, MIMO, these kind of techniques to help us to improve the system throughput. Going forward, what we foresee is due to the advancements in the material and technology, on top of just optimizing the transmitter and receiver, there is also a possibility that we can also make some changes to the wireless channel. So we call this a smart radio environment in the sense that it's not just designing the transmitter and receiver, but at the same time, we can jointly optimize this channel. We can manipulate this channel and change this channel to make it more suitable for the wireless communications. And how we can change this channel? And one of the recent technology is what we call the reconfigurable intelligent surfaces. This is empowered by a new kind of metamaterials. So if you're looking at the four small diagram at the bottom, you just imagine that this is a surface of antennas, okay, made out of new metamaterials. And this surface, you just think about it's a surface of antenna. It can perform multiple functions. For example, it can change the polarization of the radio wave. So when the RF radio wave comes in, it can change the polarization, or it can do the scattering, or it can do the focusing, which means that focus the energy of the radio wave in certain direction, or it can also just absorb the signals. Okay, it can do all kind of manipulation to the radio wave. Such design, it can be either like the discrete or continuous. Okay, like the diagram at the top left, this is an example of continuous surface, and the other hand, on the right hand side is a discrete surface, which means that on this surface there are multiple elements, and each of these elements we can controlling the on-off or maybe change the phase of the radio wave. Then together this surface will perform some functions. Let's show you some examples that will help you to understand. This is a very initial prototype built by MIT. So over here you can see this green wall. You just imagine that this green PCB wall is the surface that we mentioned earlier on. And based on the paper, this is a 3,200 antennas system. Okay, and at that time it was one of the largest antennas they ever used. So what are this surface looks like? you can see on this surface, basically 3,200 of antennas. Each of them is one dot that you can see here, either red or blue. Red means that this antenna is turned on. Turn on means that it's reflective. So whatever wave come in, they will reflect back. The other one, blue, it means that it's turned off, which means that this antenna becomes transparent and the wave can pass through. So just imagine that this is a big surface and every element you can control them by the turning on or turning off. More importantly, this surface is passive, which means that it does not transmit any power. What you do is just control each element to be on and off, like an RFID tag. So we show you an animation to see how it works. Over here, you can see this dot here on the left, this is the transmitter. And these dotted lines, green dotted lines, you assume this is the green surface. Okay. And of course, this is a 2D view. And then the target is around this direction at the lower left-hand corner. Let me play again. Okay. So what you can see, when this transmitter emit a wave, because of the green surface is on and off, based on some calculations. And what you can see is this, the energy moves towards this direction. Do you see that? Okay, which means that by controlling the elements, each of them by on and off, you can change the direction of the wave. You can reflect some of the energy back, or you can change direction, focusing on certain direction, such that most of the energy you target move towards this target direction. Okay, this is one initial idea of prototype. And later on, this group of researchers from Southeast University in China, they also come up with a prototype as shown here. You can see these two yellow-green surface, yellow gold color surface. These are two antenna surface, okay? And these two, the antennas is the so-called the RIS surface. I think like two transmit antennas. Okay, so over here you can see they use this prototype to sending two streams of data to this receiver on the right. And what you can see here is the constellation at the receiving ends. So they are sending two streams of 16 QAM. And you can see the QAM are quite nicely, they know that you're being received. And of course, this one earlier prototype, how we can use this RIS surface as a transmit antennas. And this technology also getting attention from the industry. For example, this greener wave from Europe, they've come out with this meta surface antenna as well. Okay, let's look at what they promise. Over here, you can see this, they are set up. So this is the rooms. You can see the figures on the left. This is a room without RIS. So the transmitter is inside these living rooms and receivers is along this corridor. Whereas the other scenarios is the same room set out, but then there is this RIS surface at the wall, outside the living room, okay? Over here, what you can see is the receiving end, okay, the figures on the right. Without the RIS, what you can see is this. This is the constellation that you receive, and you can see they disperse all over the space. Whereas with the RIS, you can see a very clear four constellation, which is the QPSK signals. And this demonstrates that this RIS can help you to focus the energy from the transmitter and pass the signal towards the receivers. Okay, so this is one prototype built by the industry. Next, in Japan, an NTT Docomo has also started a trial of such metamaterial surfaces quite earlier, and this is shown in 2018. So they have this big surface and they fit on a van. And they move along the van and they measuring, what is the speed of connection they can achieve. More interestingly is the test on 2020. They managed to have these surfaces which is transparent, and you can see, unlike the prototype that you see earlier on, green patch or gold color types of surfaces, this meta surface is transparent in the sense that you can use it as a windows, so the signals passing through, and at the same time you can do some manipulation. For example, focusing the signals to the end users. And again, this is one example to show how promising is this technology. In fact, this technology has been listed by this white paper by Samsung as one of the key technology that could, support or facilitate the 6G communications. And again, this paper also won the IEEE Marconi Paper Award in 2021. Okay, so I hope I give you some motivation examples, how these surfaces can be useful or, it's a promising technology. Next, we are going to introduce you our recent works on how we can make use of these RS communications, RS in the wireless communications. And we show in 3 different scenarios. One is the physical layers, is for the terahertz multi-hop communications. After that, we work on the MAC layers, multiple access, which is the layer 2, when you have multiple pairs of users try to access the channel through this RS, how we can deal with it. And then the third part, we are talking about the sensing capability of RS. If this RS surface is not just for communications, but it also has some extra capability like sensing that can sense the channel, what we can do, use it. And in all 3 cases, we adopt the AI solution. Later you can see, mainly because the problems can be quite complicated, and we show you how the AI can help us find a feasible solution. Okay, like you heard in the first presentation, moving forward, right, for example, from 4G to 5G and 6G, there's one aspect is to have a higher transmission the data rate. People expecting you are streaming the AR, VR, you are experiencing a higher data rate. And one way to achieve that is that we are moving from the radio wave, which is what in the current 3G or 4G system, move towards the millimeter wave. Because the higher frequency, the higher bandwidth, which means that you can send more information. And finally, moving forward to 6G, we may move towards the terahertz bands. But of course, moving to higher frequency band, there are challenges. One of the main challenges is the high propagation loss. Mainly because this wave, these signals can be easily get absorbed by the water vapor is in the atmosphere. So this making the terahertz communications extremely short range. Okay, the range of communication will be very short. And for us to achieve a feasible communications, we have to find ways to extend this communication range. So that's why over here, what we propose is a hybrid beamforming architecture. So through multi-hop. What you see on the left, this is the transmitter, okay? And then for us to reach the end users, of course, if the user is near, we can through the direct path. But if the user is far away, we'll need to go through the multi-hop. So over here, we assume there are multiple, this so-called RIS surface. Okay, so imagine that you have one surface here, one surface here. So the signals can bounce through the first surface and then bounce through the second before you reach the end users. And what we propose is also to reduce the complexity such that we keep only the digital beamforming in the transmitter. And all the surfaces only the analog beamforming. Okay. So what we need to do is to design these two the beamformers such that we can achieve a good signals at the receiving end. Okay. So the problem looks like this. Over here you can see we can write down the received signal to noise ratio at each users. Okay. So each users you get your received signals, and also you may hear some interference. This interference due to the signals to the other the users, and then plus the noise. And our objective is to maximize the sum rate. So typically it's the log 2 1 plus SINR. So we try to maximize this term here, which is the capacity based on the SINR. And for us to maximize this term, the parameters are this F and phi. And F is the digital beamforming, and this phi is the analog beamforming. And we try to design this tool such that this term here is maximized, of course, subject to some constraint like the power constraint, etc. To solve this problem is not an easy task. Of course, when the network is small, like one hop, we can use traditional existing optimization techniques to help us to solve it. But when the network is large, like you have two hops or more, finding a solution using existing optimization techniques will be challenging and quite complicated. So that's why we rely on the recent advancement in the AI, especially in this case, is the deep reinforcement learning to help us find a solution. In this deep reinforcement learning, there are two networks, okay? One is the actor network. This actor networks will be the network that proposing some strategy, they will design the beamformers, assign the power to find what is the best way to do the transmission. And then with this strategy, we do some evaluation. These critic networks, right, well, based on what you receive, then they will assign some rewards, okay? So for example, if this strategy is a good one, it will give a higher reward. If this strategy is bad, then it will assign a lower the reward. And through multiple rounds of iterations, then these two networks, they converge such that, we will get the optimal networks that can propose the best strategy for the wireless transmission, okay? We skip the details, we'll just show you the results. Okay, so this is the results. In this case, right, you can see the x-axis is the distance, the distance from the transmitter to the receivers. The y-axis is the throughput, okay? The benchmark is the red colors, which is this one, is the zero forcing beamforming without the RIS, which means that if we don't use the RIS, just the transmitter do the zero forcing beamforming to the end users, how it looks like. And what you can see here, this is the performance, okay? So what you can see is this. This benchmark has the poorest performance because for the same distance, it has the lowest throughput for all the schemes, okay? So this is just used as a benchmark. And then next, if you look in the blue and green, this is the case that we use one RIS, which is the single hop, okay? Which means that if you put in one RIS, the surface, so that the signals can jump over for one hop. And what's the difference between green and blue? For the blue one is the one we use the traditional optimization techniques like the alternating beam, the beamforming. And then the green one is the solution that we're using the deep reinforcement learning. Over here, you can see these two schemes, they perform quite close to one another. And in fact, the deep reinforcement learning can perform slightly better, okay? And then next, we look at the other case is the purple one. The purple one is the case with two hops, which means that the signals can jump through two RS surface before it reach the end users. For this case, right, you can see we achieve the best performance, the highest throughput for the same amount of distance. And for this case, right, the purple line is based on the deep reinforcement solution because the problem is so difficult that we cannot use traditional methods to solve it. The complexity is very high. Okay, so we can only rely on the AI techniques to help us get a solution. If you're looking at the figure on the right, this is the training the process. Okay, the y-axis is the reward functions, and the x-axis is the steps. The apples that we do the trainings. So 1,000 for 2,000, so on and so forth. This training process is trained over offline. Okay, so before you run the network, you can train this network offline. And what you can see here is these rewards get higher and higher across time and slowly will converge, which means that the network is being trained and you go further training, you don't get a higher the reward. And of course, throughout the training, you can see the rewards get fluctuation, okay? Because this is the typical AI, the behaviors. So it takes some time, the fluctuation is normal. You can see the blue cases, the fluctuation can get low, but slowly it will comes out. And for the blue, purple, and green, they're corresponding to different transmit power. So the blue case is the case with higher transmit power, and the green is the one with lower transmit power. So because for the higher transmit power, the solution space is larger, so that's why we expect a higher fluctuations throughout the trainings. Okay, so for this part, right, what we have shown here is this. Moving forward to the higher bandwidth, like the wireless, the terahertz communications, because of the short range of communications, we propose to use this multi-hop RIS to help us to extend the communication range. And we show that by using the multi-hops, we can extend the coverage by maybe 50% of coverage. And what we propose is also a hybrid beamforming solution where, with analog and digital beamforming, the digital is only performed at the transmitter and analog at the receiving end. And finally, we also propose a solution based on the deep reinforcement learning techniques to help us find the solution for this problem. Okay, so then we move on to the next topic is in the MAC layer. Okay, just now is in the physical layers like the beamforming, and it's the downlink, which means that the transmitter sent to the end users. However, in the real world, it's not just downlink, there are also the uplink, okay, which means that uplink means that the mobile, like your mobile phone, you try to send information to the base station. And because you are not alone in this network, so everyone, they want to send information to the base station. So that's why we have to deal with this so-called the multiple access, okay? So yeah, this is the motivation. And what is the new challenge that RIS bring into this multiple access is that, in the wireless network, you are not alone, okay? You are not the only one that want to access this channel. There are people around you, they also want to send information at the same time, okay? So traditionally, we try to, in the multiple access, right, we try to allocate the frequency and time resources such that all users, they do not interfere to one another, and each users, you get your own share of resources to help you to do the transmission. But with the introduction of the RIS, right, this RIS, the surface, they bring in additional challenges. So what are the challenges? One is that this RIS is also considered as a type of resources, just like the time and frequency. This RIS is a resource because it can help you to optimize your channel. So how we allocate this RIS to the end users, who can access to this RIS? So this RIS is a resource for us to allocate. After we allocate, right, we also need to optimize this RIS phase, because this RIS, remember, there are many elements. So which elements to be turned on and off, or what is the phase of each element? This is also a problems that we need to optimize. So this bringing extra challenge to the MAC protocol. We'll show you 4 different scenarios, okay, in the uplink scenarios. The first scenarios, right, is just one RIS, no single RIS, just one surface. But there are multiple transmitter and one receiver. Just like imagine that all the mobile phones try to access the base station through this single RIS. Another scenario is that with also still single RIS, but with multiple transmitter and multiple receivers through this single RIS. These scenarios you can imagine is like the drone, UAV communications, so that user 1 controlling the drone 1, user 2, they control the drone 2. Okay, in this scenario is what we have the multiple transmitter and multiple the receivers. Then scenarios 3 and 4 are similar to the first 2 scenarios, just that instead of one RIS with multiple RIS. So these are complicated problems. And how the MAC protocol design looks like, typically we can divide them into 3 scenarios. One is the centralized approach, which means that someone centrally, you optimize the resources. Okay, you can say that a time slot 1 for user 1, time slot 2 for user 2. Of course, we can also have the distributed MAC in the sense that this is not a centralized solution. So every end users, you make your own decision when you want to do the transmission. And of course, we can have a hybrid scheme in the sense that we combine the centralized and distributed. So the challenges for the MAC is like what I mentioned earlier on, is this: how we allocate this RIS, the resources, and how we optimize the RIS parameters. So over here, we consider scenarios, which is the multi-pairs communications. So there are multiple the users, they try to controlling their own drones. So user 1 control their first drone, user 2 control the second drone, so on and so forth. And what we consider here is you can see this portion is we make some assumptions. Okay, first of all, we consider a centralized solution because it's much easier as a starting phase. Then it's a schedule based, which means that someone in the central will do the scheduling. They will assign, who will do the transmission based on time. But then what we do is that we dynamically assign this RIS, okay? Dynamically, we allocate this RIS the resources to user 1, to user 2, so on and so forth. And it's for multi-pairs communication. And what we try to achieve, right, is to allocate this RIS and the RIS parameters without the power control. Let's show you an example, okay? So this is the protocol that we're going to design. Over here, you can see the x-axis. The x-axis is the time axis. So you can see this is a frame 1. You know, the first time frame, how its transition looks like. Then this is a frame 2, so on and so forth. And the y-axis is the frequency the domain. So over here, we pre-allocate, you know, the first pair, user 1 and UAV1 is using this frequency band. User 2 and UAV2 using the frequency band. So every the users, they are operating at different frequencies such that there's no interference. And what we try to do is this: how we going to allocate these RIS resources to different pairs? You know, how many pairs should we use? How many pairs should we allocate the RIS? And then what are the parameters? Okay, this is what we try to optimize. And then in this protocol, right, the first part is the negotiation phase, which I'll show you in more details. Then the second phase is where we do the transmission. So what you can see in this example is this: in the first frame, the second pair, third pair, and fourth pair, they are assigned for this RIS. I divide this RIS into 3 different groups, and they are assigned to these three pairs. Then in the second frame, I decided, you know, the best scenario is that I decide this RIS to 4 different groups, okay? So these 4 groups, these 4 pairs can enjoy the benefit of RIS, so on and so forth. Okay, the negotiation phase, again, you can further divide into 3 different steps, okay? So over here, you can see there are 3 elements: UAV and the end users, they try to communicate. And then there's this RIS, the controller. So in the step 1, right, is the synchronization, where the RIS, this is a centralized solution. So this RIS controller will broadcast some signals that consist of the pilot for these two users to do the channel estimation. Then the UAV can pass this channel to the end users, so that these users can take this chance to estimate what is the channel between the direct path. And then they will send this information to the RIS, the controller. RIS controller will do the optimization to decide, you know, how many groups should I divide, and then assign to which pair. Okay, this is done in the negotiation phase in these 3 steps. And this is how the optimization is being done. Okay, so of course there are power constraint, the RIS constraint, how we optimize the RIS phase, etc. So of course these problems you can solve using some alternating iterative traditional optimization the solution. But let's say you want to, in real time, you know, the real time, there are many drones and users, they try to communicate. So how we can find a real-time solution in a low complexity is one challenge. And that's why we propose this AI-based solution. In the sense that we call this a multitask learning. Okay, in the offline, right, we can generate many type of data through simulation. Okay, we can run the search solutions to find what is the best solution, because in offline training we don't really care so much about the complexity. And then we'll train out this learning, multitask learning, the modules. So once this module is being trained, right, in real time, based on the scenarios, how many pairs of users, what is the channel to condition, straight away we can come up with the solution. You know, how many pairs we should allocate, and which pair they will get optimized the RIS. And then this will reduce the runtime the complexity to linear. Okay, we'll show you the results. Okay, so over here, what you can see is this in these figures, right? The x-axis is the number of UAV to user pairs. Let's say 1 pair, 2 pair, 3 pairs, so on and so forth, to 8 pairs. And this is the throughput. Okay. So different lines corresponding to different RIS groups. So for the L equal to 1, which means that we allow just one group. Okay. The red one is for two groups, which means that I can cut my RIS into two groups to support two different pairs. And then this one for 4 and 8. And the red one is the benchmark without the RIS. Okay, so we can see using the RIS definitely will helps because it helps to improve the channel. Okay, so that the users can get a higher the throughput. And then over here you can see a drop, over the time. The drop is mainly because when we try to allocate the RIS to more groups, right, we improve the fairness, okay, which means that more pairs can enjoy the benefit of RIS. But because of this fairness, the total throughput of the network will drop, which means that someone that will enjoy they get higher the throughput, but overall the whole network the throughput will drop. Okay. And then if we compare this AI-based solution compared to the traditional scheme, we achieve a slightly better the performance, mainly because when we do a training, we're using the associative search. But of course, if you're comparing the complexity in real time, the AI solution will be lower than we do the optimization in real time. Okay. So as conclusion, right, we looking at how we can use this RIS to assist for multi-pairs communications. We design and propose the transmission strategy. We design the MAC protocol to facilitate this transmission. We real time jointly optimize this RIS group and also the RIS the configuration such that we can maximize the whole network the throughput. Okay, then in the last part, right, so what we're going to move forward is the spectrum learning. Okay, what is this spectrum the learning? So the whole motivation is this. So right now, what you can see the previous example, the RIS is to help us to do the communications, okay, to help us to send the information, so on and so forth. However, we are moving forward that, if this metas the surface, this RIS the surface, it is not just use it for the communications, but how about it has some kind of smart learning, such the sensing capability. It can perform some sensing, okay, and then how we can use such features. Okay, so over here we consider a spectrum sensing scenario. Why we need this spectrum the sensing? We know that RIS can achieve some performance, so on and so forth, but this may not be always the case. So for example, if one users they try to send the information, let's look at the next slide. Okay, it's easier. Okay, so let's say for this scenario, okay, these users try to send the information to the base station. Okay, you can see it may send assist by this RIS and also assist by the RIS at the top. Okay, but because you are not alone in this network, there can be someone else nearby. And let's say this user, okay, these users are sending some information as well. And if this user and the intended the user, they are close to one another. So the signals from these users may also be reflected by the RIS to the base station. And such reflection, right, because it's interfering, it's interference, we show that later on, this may do some harm to the overall the performance, because this RIS will also help to to forward this interference. Hence, if this RIS, right, has some sensing capability, it can sense that, hey, right now it's not just the useful signals, but there are some interference as well. Then we later on will show to you that maybe it's good we can just turn off this RIS. Okay, so if this RIS can dynamically turn on and off based on the actual scenarios, whether they are interference or not, it will benefit the overall network the performance. So we try to introduce some kind of sensing capability to this RIS. Over here, what you can see is this. With the offline training phase, so this offline training, basically we just train this RIS to differentiate the signals. If these signals consist of just useful signals or they consist of interference. Okay, then once this network is being trained, right, later on when in operation, this RIS can do the sensing, and based on the results, it may decide they want to turn on or off. We consider a very simple scenarios. Okay, in these scenarios, we consider just four classes. So it's a classification the problem. In the class 1, in the sense that just purely noise. Okay, no one is doing the transmission. In the class 2 means that only one user do the transmission, the user 1. The class 3 is the user 2, the user 2 do the transmission. And then the class 4 is the case that both users, they are doing the transmission. Okay, so we train this neural network to classify the scenario into 4 different classes. Based on the classes, right, if there are some interference, 2 users are do the transmission, then we do a simple on-off the control so that we just compute and estimate the SNR. If I turn on this SNR, turn on this RIS, and if turn on this RIS and the interference they reduce the SNR, then I will turn this RIS off. Okay, so it's a very simple strategy. And let's show you the results. This is a four class classifier, and we're collecting some real, some I and Q, you know, the RF signals, and then we use it to do the training. Over here, what you can see is this. For this case, we can achieve like 95% of accuracy, which means that 95% of the time we can correctly classify the channel. You know, we can know is single user or 2 users they do the transmission, or just purely noise. Then, with this sensing capability, right, we run some simulation like how if we can dynamically turn on and off the RIS, how it can be useful. So this is the scenario set up. So you can imagine that there's this building here, there are multiple RIS, and there are two users here. This user at the bottom is the desired the users. So these users will send a signal to the base station. And then there's the other one user here is the interfering the user. This user will create the interference to the signals. Okay, and this angle here, the delta, is the angle between these two users. So we can see from this figure that if this delta is very small, which means that these 2 users coming from the same direction, so high chance that these users will create the interference, because the eyes cannot differentiate the users is coming from this UD or the interference signals. So they will forward all the signals to the base station. Okay, so the base station will receive the interference. But if this angle is large, right, then RS can be turned on, because RS can differentiate these 2 signals. They can just forward the signal from UD, and then they will reject the UI signals. Okay, we'll show you the results. If you look at the figures at the top right, this is the parameters of delta, the angle just now. This is the achievable SNR. Okay. Okay, so if you look at the blue line is the case that RS always on. Okay, if I always turn on the RS, so what you can see, if this angle is small, when 2 users coming from the same direction, so you can see this SNR is very low, because the RS also forward the interfering signals. They can't differentiate the 2 signals. It will forward the interfering signals. And then as this angle get higher and higher, right? Okay, like 90 degree or even up to 150 the degree, then these 2 users are separated. Then in this case, when I turn on the IS, it will be helpful, because IS can differentiate these 2 signals. They reject the interfering signal, just forward the signal from UD to the base station. So the SNR get increased. Whereas for the case of the IS always off, right, which is the green line, okay? Because of the IS always off, so you can see the SNR does not change much. Of course, the 2 users, because based on the distance, they may impact the SNR a little bit, but because it's always off, so they don't really change much. Next, we see the red one. The red one is this, the U-shaped curve. So we can see by dynamically, you know, based on the sensing capability, I can sense, I know there's interfering or not. I can dynamically on and off the IS. So we can see I enjoy the best of both worlds. When this delta is small, I know that there's interfering, then I can turn off the IS. But then when these users are moved far away, the angle is wide apart, I can sense that, you know, even though there are interference, but the SNR is high, so I can turn on the IS. So this sensing capability will help me to decide, you know, when I should turn on and off the IS. Then I achieve the best performance. Okay, next we show you the case when we have multiple IS, okay, in the figure at the bottom. This is a case of one IS. The first three bars are the one IS, 2, 3, and 4 IS. The white color bar is the case that IS always on. Okay, so you can see this is the throughput, the SNR when one IS always on, this 2 IS always on, 3, 4, and 5. So you can see when I have more and more IS always on, it will help, okay, as the IS get increased. The reason is that I have the diversity, okay, because all the 5 IS in different direction. So definitely some of the IS will help the transmission. So by increasing the IS, it will help, okay. For the case of IS always off is the gray color one in the middle. So you can see no matter, because they are always off, so no matter how many IS, it doesn't matter. The throughput is always the same. The SNR always the same. The last case is the black solid bar. This is the case that if my IS is the spectrum learning. So you can see for this case, as the IS get increased, I get higher and higher SNR. I get the same trend as IS always on. And also for all the cases, right, with the spectrum learning, I always better than the other the two schemes, always on and always off. Because I can learn it, I can do the real-time the sensing. I can dynamically turn on and off. So I always achieve better than the other the two schemes. So for this part, with this conclusion in the sense that, we're looking at, this IS, if I have the smart capability doing the sensing, so how I can deal with it. And we show that, by doing the sensing, I can turn this IS on and off. And it will helps me to achieve a better overall system performance. Okay, I think that's all for my presentation. So these are the 3 areas that I show, how the IS can help in the future communications, and how the AI can help us to provide a solution to optimize this IS network. Thank you.
Thank you so much, Professor Yuen Chau, for your illuminating talk on AI-assisted RIS wireless networks. We'll now move on to our question and answer segment. And I believe we have a question already from our audience. And it says here, the range extension by RIS depended on the loss of RIS. What is typical loss? Professor, your thoughts?
Okay, so I think you're talking about the first topic that, if I mount multiple hops, how does it help? So, and of course, you're asking about, what happen if when I do the hopping, the signals get weakened. So, okay, so there are this problem, there are multiple aspects. So first one is this. Typically, the IS that we consider now is a passive device, which means that this IS, when we do the reflection, like focusing, etc., we are not pumping additional signals. Okay, so it's a pure passive the device. Okay, so if this is the case, right, you are right that these signals will get weaker and weaker. But because of this IS can help you focusing the signals, so then it depends on how many hops and how well you can do the beamforming. So if you can focusing the signals while you focus is higher than the loss, then by adding additional hops, it will help. Okay. Then of course we have another scenario in the sense that if this IS is not passive, if you can make it be active, it can amplify the signals, then of course it will definitely helps a lot. Okay, so I hope I answer your question.
Thank you so much. And of course, that was a very insightful answer, Professor. Now we have another question coming up, and this says, for RIS, we would need to know where is the TX and RX. Does it mean that it needs to intelligently compute and track both and direct the beam? Professor, what do you think?
Okay, so you are right that, okay, for this IS, like we shown here, for us to do the beamforming, to focusing the energies, I do need to know the channel. Okay, I need to know what is this channel from the transmitter to the IS and the IS to the end users. So I need to know all for all these channel. Okay, so I do need to do the channel estimation, and for the channel estimation, there are different scenarios. Some people they assume that I know every hops, every individual channel. There are some people they do the beamforming based on the composites channel, which means that I don't need to know the individual hop, but I need to know the overall for the channel. So these are the most recent works that people how they work on the channel estimation. I'm not very sure is there any the blind scheme, which means that the IS use without knowing the channel. I'm not very sure someone has been working on that, and then how we can find a solution. This part I'm not sure. But right now, most the literature that I have seen, we assuming that we know the channel and we need to do the channel estimation.
Thank you so much, Professor, for helping to answer that question from our audience. We have another question here, and it says, how is the channel estimated in DRL-based multi-hop RIS optimization?
Okay, so if you're talking about this work, right? For this work, we not focusing on the channel estimation. So we assume that all these channels are perfectly known, is given to us based on the given channel, how I design the beamforming. Okay, so in this work, we didn't do the channel estimation. And you can refer to some others work, that we work on the channel estimation. So in this case, we didn't solve for the channel estimation the problem. We assume it's perfectly known.
Thank you so much. We've got a couple more questions for you, Prof. This next question is, in page 38, what will happen when the desired user becomes an interfering user and the interfering user becomes a desired user?
Okay,
Yeah,
so
that's the
I think
question.
okay, so I rephrase the question based on what I understand. You are meaning that if these two users, they are both desired and they are both interfering to one another. I guess this is what you are saying. Okay, so that is not the scenario that we consider, because for the cases that you mentioned, right, both are the desired the users. By right, the map protocol should assign the resources, like different frequency or different time resources, so that the map protocol will handle that already. So the scenarios that we consider here is like this. For example, at the cell edge, this user is served by this base station, and then the users here is served by another the base station. So because we use the frequency, then they create the interference. So these are the scenarios that we consider. Because this one, by right, for the case that you mentioned, right, by right, the MAC protocol should handle that if both are desired the users.
Thank you so much, Professor, for just diving into that question for us. We have another question over here, and it says, where is the best spot for this RIS to be placed in an urban area? What do you think?
Okay. So I think is what you so this is a hard question. In fact, there are people who has done research, on the placement of RIS. Okay, so typical, the typical answer is this. We typically would like to, when you have multiple RIS, of course we would like to as diverse as possible, as you distributed them. But then for the case of single RIS, if you have a pairs, where you're going to place this RIS is important as well. And if you look at, in recently we published one of the paper. In that paper, we assume that if this RIS we hanging is in the sky, for example, carried by the hot balloon or the UAV, just an assumption. So between the transmitter and receiver, where I should place this RIS? We recently published a paper is on this topic, and it's not And actually, the conclusion is not just the placement, it's not just the XYZ, the position, but also the angle. Because this IS, you have the angle, how you going to face which direction. So it's a 6 dimension, the optimization, the problem. So you may refer to that paper to get the answer for your question. So it's a long research, the topic.
Thank you so much for addressing that, Prof. We have another question just coming up into our questions, and this is, which software is used for RIS assisted wireless?
Okay, when we run simulation, typically we use the MATLAB to run the simulation. And when you ask about the software, so usually we write our own simulation to in MATLAB or Python to run the simulation. Then of course, for the case of spectrum for learning, right? This one we use the USRP. It's a software-defined radio to help us collecting this RF trace. It's a NI-based solution, National Instrument.
Okay, wonderful. And I've got to thank the audience for just continuing to send in questions. We've got one more over here, Prof. And this one is, frequency at 100 gigahertz and above will incur huge propagation loss. Signal is not regenerated with RIS. What is the max hops supported?
Okay, so this one we don't have solution. So if you're looking at the first part, right, the solution that we show you the results is for two hops. In fact, we don't even have the solution for three hops and further. The main reason is that even just to compute the solution is too complicated. Even for example, in this case, we want to use the AI to do the training. It's too complicated for us to find a solution for more than two hops. So yeah, so I don't have the answer for you, like how many hops is the maximum, etc. Unfortunately, now it's beyond the complexity that we can solve the problem.
Thank you so much, Prof, for that answer. We have another question over here, and this one is wanting to know, our audience wants to know, is the concept of RIS viable commercially? What do you know about this, Prof?
Okay, so that's why in the first part I getting show you some examples. So we believe that this RIS is promising. So you can see that there are already real prototype that people has been doing the testing. Like Docomo, you can see there are also this surface is transparent. And this group of Greener Wave from Europe, they also have a working prototype as well. But of course, we do not know. Okay, so at least right now, what we can see is this is a promising solution that we already see a working prototype, and people has shown that this surface, this RIS can bring benefit. Okay, but eventually whether it will become a truly successful or not, I think only time will tell us.
Great. One more question over here, Prof. And this one says, what size of RIS is assumed in this simulation in page 18? The performance may be dependent on the size. What do you think the answer could be to this one?
Yeah, okay. I forget what is the size that we use in the simulation, but you are right that the performance based on the size. Okay, whether you have a small surface or a large surface. But of course, when you have a large surface, more elements, there are more parameters for us to optimize. Okay, so there's always a trade-off, because when you have more parameters for you to do the training estimation, for you to optimize, can you get a good solution or not? It's a trade-off. So I forget the size. You can check the paper, but you are right that the performance is based on the size of the surface.
Thank you so much, Professor Yuen Chau, for helping to answer all those questions from our very participative audience. I think we had almost 10 questions over there. Thank you so much for that, and of course for your illuminating presentation on AI-assisted RIS wireless networks. Thank you so much, Professor.